As promised, I wanted to make a video for my explanation of why the harmonic series diverges. I'm going to explain it 3 different ways. And I don't know, at least in the past years that I've been teaching this course, I've found that this is the thing that students like to hear me explain again in office hours, sometimes multiple times. And so if I make a video, maybe that will help. All right, so here we're introduced to the harmonic series. That is the series of 1 over n from n equals 1 to infinity. Or if you want to expand it out, it's just adding up the fractions, 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 and so on. And it turns out this diverges. And I'm going to show you 3 different ways that we can justify that basically. The first method I find really cool. Let's write out what that expansion is. And I'm going to group together our terms in that infinite sum for the infinite series in a specific way. So, like I said, we have 1 plus 1/2 plus 1/3 plus 1/4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8 plus 1 over 9 plus 1 over 10 and so on. I'll just stop there, but we'll be able to see a pattern here. Okay, so what we're going to do is compare these fractions to 1 over powers of 2. And okay, so here we've got 1 plus 1/2. Then we have 1/3. 1/3 we know is greater than or equal to 1/4. Then we have a 1/4. Then we have 1 over 5. We know that's greater than or equal to 1 over 8. Then 1 over 6, which we know is greater than or equal to 1 over 8 as well. Same with 1 over 7. And then we have 1/8. And then we can look at 1 over 9, 1 over 10. We know we've got a big chunk of fractions there that would all be greater than 1 over 16 until we get to 1 over 16 and so on. So what we can do then is we can think of the fractions in our sum as giving us things that are essentially greater than 1/2. Here we've got 1 plus 1/2. Plus 1/3 plus 1/4, that's greater than 1/2 when we add them together. And then we've got this set of terms, 1 over 5 to 1 over 8, and then we'll have 1 over 9 all the way to, maybe I'll just kind of write that in, 1 over 16. Okay, so then here we've got 1 plus, actually no, we're saying this whole sum is greater than or equal to if we replace everything with a smaller fraction, right? So you had 1 plus 1/2 plus, you can write this as 2 times 1/4 plus we've got 4 times 1 over 8, just replacing each of those fractions with 1 over 8. And then we'll end up with 8 times 1 over 16. You know what, maybe I'll explain this with an extra line. Okay, so 1 plus 1/2 plus 1/4 plus 1/4 plus the 4 1 over 8s. Plus we'll have that 1 over 16 plus 1 over 16 plus and so on. And then we're going to keep doing that forever. We can just keep getting more powers of 2 in our fractions and just keep doing that. And so the effect is then, if we look at, what we have here, we've got 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. We're now basically just adding infinitely many 1/2s to itself, right? So this is 1 plus 1/2 plus 1/2 plus 1/2 plus and so on. So we just kind of keep adding 1/2 forever. And then I guess if we're just looking at this series here, so for this series, we're saying that if we want to look at our partial sums, the sum of the first 4 terms would be equal to 1 plus 1/2 plus 1/2, which is 2. And then if you wanted to go to the first 8 terms, we'd have 1 plus 1/2 plus 1/2 plus 1/2, so 2.5, and so on. You know, S18, the sum of the first 18 terms would be 3. Then S32 would be 3.5. And we can keep going forever with that. Where basically we get the pattern that S2 to the n plus 1 minus S2 to the n is 1/2. And so if we look at just those parts of the partial sum sequence, we can kind of make a pattern here, right? Here, this S4 we could write as S2 squared. S8 we could write as S2 cubed. S16 we could do as S2 to the 4. And then we've got 2, 2.5, 3. We can then say 2 is equal to 2 plus 2 over 2. 2.5, that's like we have 3 plus 2 over 2. 3 we could write as 4 plus 2 because that's 6 over 2, and so on. So for the partial sums that are like the 2nth partial sums, we see that the limit as n goes to infinity for those partial sum terms would be the limit as n goes to infinity of n plus 2 over 2, so infinity. And one thing that I guess we haven't looked at formally about sequences is that if you've got some terms in your sequence that diverge, there's no way your whole series could, or your whole sequence could converge, right? We've got kind of a divergent subsequence is what we call it. So here we could say divergent subsequence, but you can just think of it as having a bunch of terms within your sequence that themselves form a divergent sequence, which means that the sequence of partial sums diverges. Which means that that series we were looking at, that was 1 plus 1/2 plus 1/2 plus 1/2 and so on, this series diverges. Well, in the same way that we've got, when we have two sequences and one is greater than the other and the smaller one diverges, the greater one must also diverge. We get that with series. So we can say harmonic series. We saw that that series was greater than or equal to the series that's 1 plus 1/2 plus 1/2. And if this is divergent, then we can say harmonic series diverges too. I guess another way to think about this approach too would be like saying that if this series did converge, it converged to some limit L, but then we'd always be able to create a new 1/2, right? Like we'd always be able to exceed that limit. But I guess to formalize that would be getting into like epsilon delta proofs, which we don't do in engineering math courses, only like honors math stuff. So we're good. So, okay, that's the first explanation. And I'll say intuitive explanation is that we just keep collecting new +1/2, and we do that forever. It means we go to infinity. All right, then show you a second method. It's going to be kind of like, I guess, the integral test, but before we've seen it formally. And it's again going to be kind of using this idea of comparing to something. Okay, so with our series, the harmonic series, we can think of, like, or we can represent that series on the XY plane as rectangles. So we can say we've got, I'll make it a little wider so it's easier to write on. We could say this is our A1, that's equal to 1. Then if that's A1, A2 would be equal to 1/2. A3 would be equal to 1/3. Where, like, I'm just saying that, like, the width of each of these is like 1. Think of it as like when we do, like, I guess a left endpoint situation with integration. And indeed, we will be comparing this to an integral. Okay, and then, you know, we could keep going. We could go A4 and so on. A4 is 1/4. And then a general AN. So if we are looking between n and n+1, we've got this rectangle AN of size 1/n. Okay, so then what we're going to do is we're going to compare these rectangles to the graph of 1/x. I'm going to carefully sketch that. This is 1/x. Oh, no, that's not good. It looks like it increased there. There we go. Okay, so this here is the graph of y is equal to 1/x. Well, if we consider what the sum is that we're looking for, Sn would be the sum of all those rectangles, right? If we're just looking at partial sums. So Sn would just be sum of the areas of all these rectangles. But if we look at these rectangles, all of them lie above the graph of 1/x. So all of these lie above the graph. Oops. Okay, all of these lie above the graph of y is equal to 1/x. And so if we formalize that sentence, that means that the area represented by the nth partial sum, Sn, will be greater than or equal to the integral from 1 to n+1 of 1/x dx, right? That's what this says. If we were to maybe highlight what's going on here, if in blue we have the rectangles that are representing the nth partial sum, then let's say in yellow, we've got the area under the curve, 1/x. going from 1 to n plus 1. Okay, well, this integral, we know what that is. If we evaluate that integral, let's see, so it's log x at 1 and n plus 1. Log of 1 is 0, so this ends up just being natural log of n plus 1. Okay, well, we've seen before that if the sum converges, the limit of the sum is the limit of the partial sums, right? And so we can see what we get if we just take the limit as n goes to infinity of both sides of this equation. So here we've got the limit as n goes to infinity of Sn. Based on this inequality, it must be greater than or equal to the limit as n goes to infinity of natural log of log n plus 1, but that's infinity. So diverges. Just based on the definition of divergence for sums. Now, I said 3 methods. The third one, I guess, is kind of not cheating, but going ahead, because now at this point we've also covered the integral test. So we can try using the integral test here just for practice. So for the integral test, we're looking at the sum of n from 1 to infinity of 1 over n. And so if we consider a function for this, we're looking at f of x on the interval from 1 to infinity, where f of x is 1 over x. This is continuous, positive, and decreasing. So that's good, that's fine. We love it. Okay, so then that means we can use the integral test is applicable here. And then we can say the sum converges or diverges if and only if integral does too. Okay, I guess I'm getting a little sloppy. I'm sorry, it's been a long day. Okay, so if we look at the integral from 1 to, oops, I started doing n plus 1 because I was thinking about the last thing. Okay, so the improper integral that we're doing was from 1 to infinity of 1 over x dx. Well, and I guess now this is going to be really similar to that last integral and limit we just did. Based on what we know about evaluating improper integrals, we can replace infinity with t. And then get our antiderivative, which is just natural log of x evaluated at 1 and t. And so then we have the limit as t goes to infinity of natural log, absolute value of t, minus natural log of 1, which is 0. So then this is infinity. And so this is a divergent improper integral. Therefore, by the integral test, we can also say that the sum from 1 to infinity of 1 over n diverges. There we go. So that's our 3, I guess, explanations for why the harmonic series diverges. It is a cool one because it is kind of counterintuitive. Like thinking about how adding up these numbers are getting smaller, but it just turns out that they're not getting smaller fast enough so that we can say that the whole sum kind of settles around some number. We see that we're always able to add 1/2 by just taking another bunch of sums in the partial sum bunch of terms. And then to kind of compare for the example that we saw, do you see? yes, here, the P series. The P series, the sum from n is equal to 1 to infinity of 1 over n to the p, it converges for p greater than 1 and diverges for p less than or equal to 1. Where p is equal to 1 is the harmonic series that we just saw. And so then if it was, instead of 1 over n, 1 over root n or something like that, that will also diverge. But then if it was 1 over n squared, or even 1 over n to the power of like 1.000001, because that's still greater than 1, we get a convergent series. Isn't that interesting? Okay, I'll end this here so I can upload the notes, and I hope you like this. I don't know, this explanation here with like the adding up these things to get 1/2 is, I don't know, I think it's kind of cool. Anyways, okay, bye.